Okay, so sound waves carry energy that can do work. The amount of energy transported per second equals power, as we already know. As sound moves away from a source, it spreads out over a larger and larger area. So here's a sound source. You can see how the sound gets dispersed as we spread out over a larger area. As the area gets bigger, the intensity at one point is less. And the P stands for power, and the A stands for area, and the I stands for intensity, the intensity of the sound. And we use these units, watts per meter squared. Now, sound is transmitted uniformly in all directions. The areas of the surfaces become spheres. And the area of a sphere is right here. Remember, a sphere is kind of like a ball. And the radius, of course, would be right here from the center to an endpoint. Intensity is proportional to the square of amplitude. You're given all the units right here. Delta P is pressure amplitude, P is density of the medium. We're not going to really get into that because that form is a little wacky, I think. So, but we could probably do, yeah, we'll probably skip that formula. So let's look at the example down below. So any questions so far? And again, I'm just going to cross out this formula. We're not going to really use this one. Okay. So you and your friend are watching fireworks that are launching from the observatory. You are standing right in front of Berman Hall, 150 meters, and your friend's across campus, whatever that is, 700 meters. The sound intensity at that point is 0.2 watts per meter squared. What is the sound intensity of your location? How much power is a firework emitting? So intensity, again, excuse me, is power over area. So our intensity, of course, is 0.2. And we're trying to solve, sorry, actually, we want the intensity. No, we are solving for power first. So you gotta get the power of the source. That's what P represents. So we'll look at your friend first. The intensity at that point is 0.2 watts per meter squared. So this is for your friend. And the area, so it's how far they are from the source. So it's 4 pi and 700 squared. So you would assume that the source is going to be right there in the middle, and your friend's at the end of that sphere, which is 700 meters away from the source. So you solve for the power, and if you solve for that power correctly, you should get 1.23 times 10 to the 6 watts. Now, what's the intensity at your location? So it's still the same power, but now you got to solve for your own intensity. So your power times your area. Now you're 150 meters away from the source. And if you work that out, you should get, I believe, 4.36 watts per meter squared. So it's going to be more intense because obviously you're closer to the source compared to your friend who's at that location. Any questions so far? Okay, let me go on clear. Sound level and decibel. So this is going to be important before we move on to 7.5 on Doppler effect. So unit of measure that's used to compare two sounds, or sorry, that's what a decibel is. A decibel is unit of measure to compare two sound intensities. So based on how human perceives loudness, and if you double the intensity, the sound is not necessarily twice as loud because it's on a logarithmic scale. So actually, if you think about it, that's log base 10. So if you double the intensity, I believe actually, if I think about this correctly here, log base 10. Yeah, it's kind of a fraction. What you expect. Beta's intensity level, I and I0 intensity of two sounds, and I0 is usually going to be, I believe, 1 times 10 to the negative 12 watts per meter squared. Intensity level is 0 only means that I equals I0, and log base 10 of 1 is just 0 in that case. Intensity can be measured. And allows simply how your ear perceives the sound. And doubling intensity does not double loudness. So what we see is that the sound intensity actually goes up by 10 because these are all powers of 10. So for example, the faintest sound you can hear would be right there. Rustling of leaves is that. A whisper at 1 meter's distance is that. A quiet home, but you might hear some, maybe the air conditioner or some other things. Average home, average office, soft music, normal conversation gets a little louder. Noisy office, of course, is that. Loud radio or classroom lecture. If you're in a heavy truck, noise factory. Once you get past 100, that's when you can start damaging your ears. A loud rock concert obviously is not good. and that's kind of threshold pain. And then jet airplanes or burst, well, that would be horrible. Would be all that. So that kind of gives you a good idea of what we expect with intensity of sounds. And again, it's given by this formula. So let's look at some examples that deal with that formula, and then we'll move on to Doppler effect. Any questions so far? So again, taking a look at this right here. And if I0 is 1 times 10 to the negative 12, and say you're talking about normal conversation, 1 times 10 to the negative 6, and if you were to work all that out, you would get 60 decibels. So let's let's look at a couple examples here. So you double the intensity of sound coming from stereo. What is a change in loudness? Okay. So beta equals 10 decibels times log of I or I0. And if you double the intensity of sound, there's the I equals 2I0. And those cancel. 10 times log of 2, and use a calculator. You should get, and I actually have a calculator here. At least so I thought I had one. Oh, there it is. Yeah, you get about 3.01. And we use dB as decibels for the units for that. So it's not terribly loud. Or change of loudness is not that much. Experiments show that the density level increases by 10 decibels. The sound will seem twice as loud. So, so what's the intensity of 20 decibels? And by the way, if you do increase it by 10 decibels, that would make sense that you're doubling because you're doing log base 10. So let's look at the next one here. Beta equals 10 times log I over I0. And the intensity is 20 decibels. Excuse me. Sorry, you want to find the intensity at 20 decibels, so the sound level's at 20. So it's 10 times log of I. Remember, I0 is 10 to the negative 12 power. And if you do 20 divided by 10, so 2, that's base 10, so it becomes 10 squared. So remember how logs work. So I is going to be 1 times 10 to the negative 10 power. And that'll be the intensity of the sound. So we see, and that's watts per meter squared. Yeah, so we see that by increasing by 10 decibels, we actually see 100 times increase for the intensity. So we won't do any the homework problems down below. Let's now move on. Let me actually, give me a second here, guys. Oh, sorry, it was just really loud in the other room, and ironically, I couldn't hear myself think, right? Here we are talking about sound. So my apologies about that. Okay, so let's move on to 7.5. And we'll start moving to Doppler effect. So again, the key takeaway that we talked about here was 7.4 was we talked about intensity and how that could change and how it compares to loudness. So I'm going to clear all this. That was one of the forms we talked about over here. Okay. But we won't do these problems here. We'll just kind of forego that and move on to Doppler effect. One sec. Okay. So Doppler effect. So Doppler effect is kind of an important topic. It's pretty relevant because, like, for example, let's say you're stopped at a stoplight and you hear a fire truck coming from behind you. Of course, the sound gets louder and louder and louder, right? So you kind of know to get out of the way. Or say, for example, you're driving north in El Camino. So you're leaving campus heading towards, like, say, San Mateo. And the opposite direction, the southbound direction of El Camino, you see a fire truck. Of course, you'll try to get out of the way because you don't know, or stop because the fire truck might turn left and, you know, you don't want to get in the way of the fire truck. But obviously, the fire truck is going to be, the sound's going to get more intense. But then after it passes you and then you kind of just keep going forward, that sound gets less and less intense. So we're just going to talk about how that all works from a mathematical viewpoint. So, so first of all, we're focusing on a source of sound that moves by a listener. That's what Doppler effect's all about. High pitch. So the pitch gets high, you know, when it's coming towards you. And low pitch when it's leaving. And remember we talked about, like, condensations of sound. So here's a truck at rest, and obviously a person that's standing right there. And then when the truck's moving, obviously the wavelengths get smaller and smaller, meaning the frequency gets higher. And remember, high frequency is high pitch. And the formula is this right here, where FO will be the frequency heard by the observer. . . . Fs will be the frequency of the source. Excuse me. VO will be the velocity of the observer. So for example, if you're driving the car, you'd be the observer, so your velocity. Vs will be the velocity of the source. And VW will be the velocity of your sound wave. Looks like I just got disconnected. Let me use my hotspot. Okay, hold on a sec. Okay, using my hotspot. Sorry about that. Looks like I lost my connection there. Good thing it was recording, but I'm going to redo that part of that lesson. So let me share my screen again. Okay, let's try this again. Okay, so again, Doppler effect basically deals with a source of sound that moves by a listener. High pitch is when it's coming towards you. And low pitch as the source is leaving. Or high pitch is high frequency. Low pitch is low frequency. Again, FO is a frequency that you hear because you're the observer. Fs is the frequency heard by the source. Sorry, the frequency from the source or of the source. Good, looks like we're still recording. Excuse me. VW is the velocity of your sound wave. Vs is velocity of the source. And VO is the velocity of the observer, of how fast you're traveling. Or if you're at rest, then of course, that'd be 0. Excuse me. We assume that VW, VS, VO are signless, don't have any signs at all, so you don't worry about pause or negative. And you use a top sign when the object is moving towards you. Or towards the other object. When things are getting closer. Okay, so that's the formula right here. For the Doppler effect. Okay, so now we're ready to do a couple problems. I'll have you guys try some in breakout rooms after that. So I'll go ahead and clear this. So let me recopy the formula here. Okay, you are driving down the road 20 meters per second. You approach a car going the other direction at 15 meters per second. with the rate of playing loudly. If you hear a certain note at 600 hertz, what was the original frequency? So, so this is what you hear, right? So that's FO. You want to know the frequency of the source, because that would be its original frequency. So 600 equals Fs, which you're trying to find. We're going to assume that speed of sound is 343 meters per second. It really depends on the temperature and the air or the medium it's going through, but we'll do 343. And now because it's going to, it's coming at you, right? Because you're approaching it. So you use the plus sign, using the top sign, plus 20, because that's your velocity of the observer, minus the source. If you work all this out, all that big fraction becomes 1.1. So the frequency of the source, of course, 542 hertz. So that's how you would tackle a problem like that. You just use the formula above, realize what you got, and then solve for what you're missing. Now, the next one I think is a little bit cooler because you are trying to find how fast something's moving. So a duck is flying overhead while you stand still. As it moves away, you hear it quack 190 hertz. Because you are a brilliant naturalist, you know this type of duck quacks at 200 hertz. Fine, whatever. How fast is the duck flying? So you're standing still. So you're going to be the observer. This is the velocity of the source. This is the frequency of the source. And that's the frequency that you hear. And we'll use VW equals 343. So remember, FO. Now it's going away from you. So use the bottom signs now. So minus VO and then VW plus VS. Frequency of observer, of course, is 190, the frequency that you hear. And the frequency of the source is 200. 343 minus 0, of course, doesn't change anything. 343 plus VS. And at this point, it just becomes algebra. You really just have to just go about the algebra correctly here. And just trying to think here. Yeah, you could probably cross multiply. So 190 times 343 plus VS equals 200 times 343. So this right here is being multiplied by 190. If you work everything all out correctly, I trust you guys can do the algebra. VS equals 18.1 meters per second. And again, you just kind of just go through all the algebra, distribute here, distribute there, work it all out. So any questions about these two examples? Nope, okay. So now, I'm gonna have you guys try some problems in groups. Now we'll spend maybe, maybe 15 minutes or so doing these problems. Let's take a look here. I'm gonna clear this. Stop sharing. Stop